Hello Bearcats. In this session we're going to learn about radian and degree measure. We're going to begin the wonderful world of trigonometry, and we're going to start with the measure of angles and how they are measured. So I want to talk to you first about this angle, and this little point is called the vertex, which is mostly a review for you. Also, I want to talk about the angle if it moves counterclockwise. It's called a positive angle. It begins at the initial side and it ends at the terminal side. And these are all really important. So this is a positive rotation. It could also look like this, and will look like this mostly as we use the unit circle. We would begin here, and this would be our initial side, and we would rotate counterclockwise, which is to be a positive rotation. Oops, didn't do that very good. Positive rotation, sorry, that would just be considered the center, and this would be your terminal side. So this would be the initial, and this would be your terminal. And the angles can be, this happens to be a positive rotation. And there are several Greek letters and things that are used to represent the angle. Most often you're going to probably see theta, but you will also see alpha, and you'll also see beta. And you can also see capital letters A, B, and C. But more often than not, you'll see theta. Theta always represents an angle measured in radians, by the way. The next thing I want to talk a little bit about are positive and versus negative angles, and how we can talk also about coterminal angles. So let's go ahead and move on. Make sure you have all the notes for this section. Thank you. Okay, as we go here, I want us to talk about, this would be our initial side, and we would rotate in a positive rotation counterclockwise. This would be, we're going to call this angle alpha, and this would be a positive angle. If we started at the same spot, so we had our same initial start, and we rotated in a clockwise direction, but we had the same ending spot, or the terminal side, so we have the initial side and the terminal side, this would be a negative angle. And we'll call this one beta. Okay, these two angles, in this case, alpha and beta, are coterminal. And they're coterminal because they have the same initial side and the same terminal side. Now I want to give you just a little bit of a sneak peek here, because our circle we can rotate over and over again. So if I initially start here and I rotate all the way around to here, that would be a positive angle, and we'll call that one alpha. If I start right here and I rotate, let's change colors to make it a little bit more obvious. Let's see. All right, so if I start here at the same terminal spot, but I rotate in a opposite direction, and it would be a negative angle, and we're going to call the red angle beta, then alpha and beta are also coterminal, because they both start at the same place. Alpha begins here at this terminal point, and this ends at this terminal point, and it has to be the same terminal point to be coterminal. I'm going to give you some help in how you determine coterminal angles from a given angle without actually seeing a picture. So I want you to write all of this down, and the next thing down too. Go ahead and pause if you need to. Go Bearcats. Okay, coterminal angles are found by adding or subtracting 360 degrees or 2 pi, which both of those are one full rotation of a circle, from a given angle. So it's very important if you're asked to find the coterminal angle, you know, you can add 360 or multiples of 360 degrees, or 2 pi if you're given radians, or multiples of 2 pi to get a, add or subtract that to get a coterminal angle. Okay, that's very important. Next, we're going to discuss radians. We looked at that on Friday a little bit. We're going to go back and look at our degrees and radians again on when we get back to class, probably every day for the next few days. But I also want to give you some more definitions about radians. Okay, 1 radian is the measure of a central angle, which we're going to represent by using the symbol theta, that intercepts an arc. S is the arc, equal in length to the radius. Radius is represented by r of the circle. And we talked a little bit about this on Friday. So if this is the radius of my circle, and I rotated along the outside of the circle that same distance, the distance of the radius, this is r, and I rotated that same length, let's say that is r, and I didn't do a very good job on here, sorry about that. Okay, so this would be s, this is the arc would be s, but it would be equal to the length of r, okay, and this is also r, and this angle would be theta. So in this case, theta, the angle, would be equal to the arc length s over r. And in this case, if a central, for a unit circle, 1 unit, this would be 1. If r was 1 and s is 1, that would be, the angle would be 1 radian. Excuse me. All right, I'm going to do just a very brief review of some of the key points on the unit circle, but we're going to review that every day in class, and you need to review that on your own as well. Then we're going to go on and talk about complementary and supplementary angles, degree measures, arc length, and then some other formulas. So let's go ahead and do a slight review. Make sure you have this written down. Okay, the other day we started with our big 4, and remember that's going to be 0 degrees, and then of course 90 degrees, 180 degrees, and 270 degrees. To match up with radians, oh, and this would be 360 degrees. To match up with radians, this would be 0 radians. Remember that 90 would be half of a semicircle, and so this would be pi over 2, since 180 degrees is pi, so half of pi. And if that is 1/2, then pi is really 2 halves, or 2 pi over 2, and therefore 270 is actually 3 pi over 2. 360 would be 4 pi over 2, or that reduces to 2 pi. All right, so there's some things. If you got this on Friday, then you're in probably pretty good shape. Remember, the next thing we do are the 45-degree angles, the one that splits the angle in half. And I'm not going to do them all. Just going to remind you that this is 45 degrees, and that 45 degrees is actually pi over 4 in radians. So it's 1/4 of the semicircle. After that, we did our 60 degrees, and remember our 60 degrees, all of these reference from the x-axis, from this axis right here. So this is the 45 degree, this is the 60 degrees. So this is 60 degrees. That means the 60 degrees are up here by the y-axis, so they would be 60 up here, and it'd be a 60 up here because it would be 60 degrees from the x-axis. It'd be 60 down here because it'd be from the x-axis, and it'd be 60 down here because it'd be from the x-axis. 60 degrees is actually 1/3 of a semicircle, or pi over 3. And then finally we do our 30-degree angles, and our 30-degree angles are the ones close to the x-axis, and you'd have 4 of those, and that's our 30-degree angle, and that is 1/6 of a semicircle, or pi over 6. We will practice our whole unit circle and finding our degrees and radians over and over, and have a little quiz later in the week. All right, let's move on now to complementary and supplementary angles. All right, let's some of these are a review. Of course, complementary angles add up to 90 degrees. If no one's ever told you this, a complement is the right thing to do, and so 90 degrees would be a right angle. Or in radians, that would be pi over 2, or pi over 2. Supplementary angles add up to 180 degrees, or up to pi, and you would have to use radian measures. We're going to do using a lot of fractions here, so you'll have to do a lot of common denominators, but I know you're really good at that by now. All right, next would be how we convert something if we don't know it, if it's not something of special angle that's on our unit circle. Most of those, by the time you finish this week, you will know those. But let's say it's not an angle that is on our unit circle. It's not one of our special angles, our 30 or our 45 degree or a 60 degree reference angle. Then you would want to know how to convert degrees to radians and radians to degrees. If you're going from degrees to radians, you would multiply by pi over 180, and that will give you radians. If you're going from radians to degrees, you'd multiply by 180 over pi. Think about your radians at the top, your radians at the bottom. They would cancel, and you'd be left with degrees. That would give you your degrees. And over here, you have your degrees at the top and your degrees at the bottom. They would cancel, and that would leave you with radians. Those are very important formulas. You want to make sure you have those written down. Also, arc length. We discussed arc length a while ago, and this is a formula that you're going to want to know, and it's just rearranging the other one. What we discussed a while ago was that theta equaled S over R. Theta equaled S over R, which was the arc length over the radius. But if we want to solve for arc length, then we would have S, which is our arc length, equals R times theta. And that's a very important formula that you will want to know how to use, and that will give you the length of the arc, or the part of the circumference of a circle. All right, last we want to talk about some linear angular speed formulas and the area of a sector. Please make sure you have all these written down in your notes, and you're going to be able to refer to these. They need to be in front of you on your desk so that you can use them for our practice in class. All right, to wrap this up, linear speed, the formula for linear speed, V represents linear speed, and V is equal to the arc length, the arc length divided by time. And you know from earlier that arc length is represented by S, so S divided by T. But you need to keep this really in front of you. Until you use this enough, you really won't remember what these letters represent. So you want to, every time you write them down, then write what their meaning is, and it'll help you. By the way, linear speed measures how fast, gosh, I'm not writing very well, how fast a particle moves along a curve. So measures how fast a particle moves along a curve. Okay, so in other words, let's think of a bicycle tire, and let's say a rock gets stuck in your bicycle tire, and linear speed will tell you how fast that rock is moving around the tire. All right, next, angular speed. Angular speed is represented by W, and it is the central angle, which we usually represent by theta, and theta is always measured in radians. If I didn't say that earlier, theta will always be measured in radians. So it's the central angle divided by time, which is theta divided by time. And again, you're going to want to have these formulas in front of you. And the angular speed measures how fast the angle changes. And we'll get a chance to look at some examples of those in the real world. All right, and finally is the area of a sector. I know you've done this before. The area of a sector of a circle, let's say that would be the entire area. So it wouldn't be the arc length. The arc length is on the outside. It would be the whole shaded region, the whole little piece of pie, so to speak. And that formula is A equals 1/2 R squared theta. And again, theta must be measured in radians. After this unit, you really will be dealing with radians, I would say 99% of the time. For this unit, though, we'll still be dealing with degrees some. Okay, hope you all have a great evening, and go Bearcats!